provided by Thomas Allgaier and Frennis, based on the most relevant LinkedIn posts about software-defined and AI-defined vehicles in calendar weeks 29 and 30. Frennis supports Tier 1 automotive suppliers with early-stage market validation for their R&D efforts by combining secondary research, direct OEM expert interviews, and facilitated customer meetings. You can find more info in the description. So welcome to the Deep Dive, where we are unpacking the top discussions for mobility professionals across LinkedIn for you today.
Yeah, thanks for having me. We're really looking at a massive evolution right now.
We really are, because, a single line of compromised code in a modern vehicle now costs automakers an average of $10.7 million per incident.
Right.
Which is just wild.
Oh, it's staggering. And I mean, that 10.7 million figure, that is just the financial fallout.
Right.
It doesn't even touch the brand damage or, the actual physical safety risks on the road. The fundamental architecture of the automobile is essentially being ripped apart and rebuilt from the ground up.
It's like we aren't even building cars anymore. We're basically building these highly vulnerable server racks on wheels, right?
Pretty much, yeah. And the people designing these systems are out there trying to build the airplane while they are flying it.
Exactly. Yeah. Which is our mission for you on this deep dive. We are cutting out the fluff, and we want to look at the raw mechanics of this shift from the software-defined to the AI-defined vehicle. We'll be hitting the architecture, the cascading safety threats, and how OEMs are actually attempting to execute this stuff.
Yeah, and the terminology itself is shifting so fast that even the supply chain can barely keep up. If you trace the chatter back to CES 2026, the industry has definitively moved past software-defined.
It's totally shifted.
Right. Now it's the AI-defined vehicle. And some practitioners on LinkedIn are even pushing it further to call it the experience-defined vehicle.
See, that sounds kind of like a marketing pivot to me.
It does sound like it, yeah.
Yeah. But I want to break down what AI-defined actually means for an engineering team, working on a random Tuesday morning. Because you can't just slap a larger zonal compute unit into a chassis and suddenly call it an AI vehicle.
No, you really can't. There has to be a mechanical shift in how these entire systems are built. And it all really comes down to this core concept called decoupling.
Decoupler.
Because fundamentally, automotive engineering has always been trapped by silicon timelines. Historically, you couldn't effectively test your software until the physical hardware, like the system on chip, was actually manufactured and sitting physically on your test bench.
Which is a massive bottleneck.
Exactly. You were entirely bottlenecked by hardware availability, but decoupling completely shatters that dependency.
And they are doing this using virtualization, right? Because the sources mention these approaches, like EB-Civion being deployed to decouple cockpit software development from those physical hardware timelines.
Yeah, EB-Civion is a great example.
So how does that actually work under the hood?
Well, think of it as creating a flawless digital twin of the hardware's architecture. Instead of waiting for a physical chip from Qualcomm or NVIDIA, the engineering teams use a hardware abstraction layer in the cloud.
Oh, so it's all cloud-based simulation.
Right. It simulates the exact instruction sets, the memory constraints, everything of the future physical chip. So the software developers can write, compile, and aggressively test that whole digital experience in a virtual environment.
That makes total sense. So by the time the physical boards are finally minted, the software is already completely mature.
Exactly. It speeds up the iteration loop immensely.
Okay, so that handles the software side. But to actually run that software in the real world, the physical nervous system of the car has to change too, right?
Entirely.
Because the sources note that General Motors is adopting an Ethernet backbone for their zonal architecture. And I kind of think about it like this. We're moving from a traditional CAN bus, which kind of broadcasts messages to every component, like a localized neighborhood dial-up network.
That is a brilliant way to phrase it, yeah.
Right. And we are moving to a native Ethernet backbone, which acts way more like a citywide fiber optic grid routing massive packets of data instantly.
You have to. I mean, the bandwidth requirements for AI inference make that upgrade completely non-negotiable at this point.
But wait, you can't just rip out 50 years of CAN bus architecture overnight. How do you integrate this massive Ethernet backbone when half the car's components are still running on legacy telematics and simple microcontrollers?
Well, the secret is you don't actually rip it out. You build a hierarchy. So classic AUTOSAR's layered architecture remains the baseline for those basic functions.
Oh, I see. So like your power windows and seat motors?
Yeah, they're still using that legacy communication. They don't need fiber optic speeds to roll down a window.
That makes sense.
But for the massive data pipes, like the programmable perception networks, that's where the new IE 802.3D meter standard comes in.
Okay, let's break that standard down a bit. How does IE 802.3D meter handle the data differently to eliminate the bottlenecks?
So it creates native Ethernet nodes specifically designed for those perception networks. In a legacy setup, a camera sends raw data to a central gateway, which then has to translate it and route it.
And that translation creates latency.
Exactly, creates a delay.
Right.
But this new standard allows the cameras, the radar, the LiDAR, to plug directly into that high-speed Ethernet grid as native nodes.
Oh, wow. So they are speaking the exact same packet-switched language as the central AI computer right out of the gate.
Precisely. No translation, no bottleneck. And automakers are actually being scored on this transition right now through a new AR0 to AR5 framework.
AR0 to AR5, what does that measure?
It grades their electrical and electronic architecture consolidation maturity. So it's a huge metric right now.
But consolidating all that compute power into a central brain has to introduce a massive physical constraint, right? Heat. The sources highlight that thermal management is being completely reframed.
Oh, it really is. It's no longer just about keeping a combustion engine from overheating.
Right, because engine heat is distributed across the block. But AI compute heat is incredibly concentrated in one spot.
Exactly. When you are running heavy machine learning models on a centralized system on chip, you generate these intense localized heat fluxes that traditional automotive liquid cooling loops just aren't designed to handle.
And if the chip gets too hot and thermally throttles, what happens?
Well, your autonomous driving system starts losing frame rates.
Which is terrifying at 70 miles an hour.
Right. So thermal management is now this huge strategic enabler. Superior cooling literally translates to higher autonomous performance.
Wow. Okay, so you've built this high-speed fiber optic city on wheels, and you've cooled the central brain enough to run these massive AI models. But that creates an entirely new problem. By networking all these previously isolated systems together, a single broken lock can compromise the entire city, right?
Oh, absolutely.
The attack surface isn't just a single ECU anymore. It is literally the entire vehicle.
Which is exactly how we arrive at that $10.7 million average cost per cyber attack we mentioned earlier.
It's all connected.
Yeah, these advanced networks mean vulnerabilities cascade instantly. A hacker gaining access through, say, a simple Bluetooth module can pivot across the Ethernet backbone and go straight into the braking controller.
Man, that is scary.
It is, and it's forcing a complete collision between two historically separate engineering disciplines, functional safety and cybersecurity.
Because those used to be entirely separate silos. You had the safety team over here making sure the brakes didn't physically fail, and the security team over there making sure nobody hacked the infotainment screen.
Exactly. And now, the practitioners on LinkedIn are showing major friction on the ground as those two teams are forced to merge.
Where's that friction coming from, mostly?
It's largely driven by standards overlap. People are highlighting this really confusing terminology clash between ISO 26262, which governs functional safety, and ISO 21434, which governs cybersecurity.
Oh, I bet that's a nightmare for the paperwork.
It really is. Both frameworks demand rigorous risk assessments, but they use similar words to mean very different things. It creates massive integration headaches in the engineering base.
Well, let's dig into the functional safety side for a second, because there was a post by Aladadine Hamdi that provided a really clear breakdown of how ISO 26262 utilizes ASIL classifications to grade risk.
Yes, that was a great breakdown.
He explained how it scales from ASIL A up to ASIL D based on three factors: severity of the failure, exposure to the driving situation, and controllability by the driver.
Right, and ASIL A is pretty straightforward. Think of your automatic windshield wipers.
Right, if they fail, you just turn them on manually.
Exactly. If the code crashes, it's annoying, perhaps slightly hazardous in a heavy downpour, but the driver has high controllability. They can easily reach out and fix it.
But then you jump up to ASIL D, the most demanding tier, and that covers critical systems like electric power steering, brake-by-wire, and these high-speed ADAS functions.
Life or death systems, yeah.
Exactly. So to achieve ASIL D compliance for a central compute architecture, what are the actual mechanics involved? I mean, you can't just rely on writing bug-free code, can you?
Not even close. ASIL D requires hardware-level fault detection operating in milliseconds. And the primary mechanism for this is lockstep processing.
Lockstep processing.
Yeah, you physically have two CPU cores running the exact same mathematical operation simultaneously. And there is a checker circuit that compares their outputs every few nanoseconds.
Every few nanoseconds? That is incredibly fast.
It has to be. If a cosmic ray flips a bit, or a software glitch causes a microsecond discrepancy, the system instantly detects the fault and triggers a safe state protocol.
Like safely pulling the car over.
Exactly. But it demands massive, expensive hardware redundancy.
Wow. And hey, quick interjection. If you're finding this deep dive into ASIL and network vulnerabilities valuable, make sure to subscribe so you catch our future editions. But returning to the safety aspect, there is another standard to consider here too, right?
Yes. It is also vital to separate that kind of internal hardware failure from SOTIF, which is another standard heavily discussed in the sources right now.
How does SOTIF differ from ASIL?
Well, ASIL covers internal failures, like a broken sensor wire or a crashed CPU thread. But SOTIF covers failures stemming from external real-world performance limitations where the hardware actually works perfectly fine.
Oh, I see. So it's kind of the difference between your eye muscles physically tearing, which would be an ASIL failure, and simply being blinded by walking out of a dark movie theater into the blazing sun.
That is an excellent way to conceptualize it, yeah.
That would be SOTIF. Your eyes work perfectly fine, but the system is entirely compromised by the environment itself.
Exactly. If the camera is blinded by glare, or the radar gets confused by a chain link fence, the software didn't crash, but the vehicle still fails to brake for a pedestrian.
Right. The outcome is still a disaster.
Exactly. And because these systems are now centralized on that Ethernet backbone we talked about, the stakes for both ASIL and SOTIF failures are just exponentially higher. Security researchers have already demonstrated the remote manipulation of steering and braking over compromised CAN bus networks.
Which is exactly why regulators are paying so much attention to that threat vector right now. The sources mention the U.S. Senate Commerce Committee unanimously advancing the Connected Vehicle Security Act to address these software vulnerabilities at a federal level.
It's a much-needed step. But the industry is also trying to get ahead of the curve mathematically, too. There is currently a feasibility study on AUTOSAR QCL, which is exploring the integration of quantum-safe cryptography.
Wait, really? Quantum-safe cryptography in cars?
Yeah, they're actively engineering the encryption layers today to protect against future quantum computers that might be capable of breaking current vehicle key exchanges.
That is wild to think about. So, okay, we have designed a quantum-resistant ASIL-D certified supercomputer on wheels. The theoretical engineering is sound. But who actually owns the code running on it?
Ah, that is the trillion-dollar question, or rather the half-trillion-dollar question.
Right, because whoever owns the technology layers captures a massive piece of this automotive software and electronics market. And the sources project that market to hit $519 billion by 2035.
$500 billion. That number is completely rewiring legacy business models as we speak. But capturing it requires seamless integration.
Which brings up Aniruddha Doral's post, right? He mapped out what he calls the 5-stage platform journey.
Yes, Ani Dural's breakdown is great. It highlights a really critical reality. Automakers simply cannot build everything from scratch anymore. The time to market is just too punishing.
So what are they doing instead?
They are relying heavily on pre-certified, off-the-shelf software features for ADIs and over-the-air update mechanisms just to accelerate from the engineering phase to launch.
Because automotive competitiveness is no longer about who can stamp steel the fastest. It's basically a turf war over layer ownership.
Exactly.
But attempting to build those operating layers entirely in-house has been pretty catastrophic for some legacy players. I mean, look at the collapse of the automated driving alliance between CARIAD and Bosch.
That collapse is a textbook example of the friction we are discussing. I mean, you had billions in losses and severe validation shortfalls.
Oh, what wrong there?
Well, when you try to merge legacy Tier 1 supplier code, which was built for isolated microcontrollers using rigid waterfall engineering, with modern, agile software development loops meant for central compute, the hardware abstraction layers just break down.
So the integration complexity basically swallowed the project whole.
Exactly.
So if two giants like that, with virtually unlimited resources, are stumbling over integration, who is actually managing this platform complexity well?
It is playing out very differently across the major OEMs. If you look at Volkswagen, a significant portion of their current cost disadvantage is being attributed directly to platform and software architecture complexity.
Really? So it's not factory inefficiency?
No, the struggle to unify the software layer is physically bogging down their hardware output. Conversely, you look at BMW, and they are taking a totally different approach.
What's BMW doing?
They're building vehicles like the iX3 and the X5 on completely divergent physical hardware platforms, so one electric, one combustion, but running them on an identical software architecture.
Oh, wow. So they write the code once, push an over-the-air update, and both the electric and gas SUV get the new interface.
Right. They're successfully decoupling the digital platform from the physical platform constraints.
That is smart. But for the heavy lift layers that automakers just can't efficiently build themselves, like mapping, natural language processing, deep autonomous driving data sets, we are seeing massive concessions to the tech sector.
Oh, absolutely. The tech giants are effectively colonizing the vehicle's experience layer right now.
Yeah, I mean, Ford is integrating Apple Maps natively into its next-generation EV platform starting in 2027. Mercedes-Benz partnered with Google Cloud to power MB.OS. Stellantis joined Mobileye's RM network.
And you have to contrast those legacy tech partnerships with the strategy of Chinese EV challengers like XPeng.
Right, they just unveiled their LO3 SUV in Munich.
Yeah, and they aren't trying to capture the European premium segment by just undercutting on price or battery costs. They are targeting that market purely on the strength of their software and design. The software itself is the luxury differentiator.
Which perfectly pivots the conversation from boardroom strategy to real-world execution, because the dividing line between surviving this transition and falling behind is entirely dependent on over-the-air execution, right?
The TA is where the rubber meets the road, yeah.
And it has historically been a massive advantage for pure-play EVs like Tesla over legacy OEMs like Ford. But Ford is adapting. The sources highlighted a recent Ford Pass update that totally revamped remote vehicle controls.
Yeah, that was a big deal.
They moved to slide-based interactions and integrated weather-aware climate settings. It sounds super simple, but refining that user experience layer is incredibly difficult for a legacy hardware company to pull off.
It is, because that user experience dictates your premium pricing power today. Consumer surveys consistently show that assisted and autonomous driving capabilities are replacing traditional luxury metrics.
People don't care about the engine size anymore.
Right. Consumers care way less about engine displacement and more about how much of the tedious driving task the AI can handle for them.
Though, the economics of total autonomy, like the robotaxi market specifically, they are currently burning massive amounts of capital. The business model isn't even settled yet. Are you charging per fare like an Uber? Are you selling a subscription, licensing the stack?
Or do you take on the astronomical capital expense of owning and maintaining the fleet yourself? The capital required to survive the EV and autonomy transition is just brutal right now. If you look at the challenger space, Lucid's per-vehicle losses currently far exceed NIO's.
It's a tough market. But let's set the financial burn rate aside for a second, because there is a much deeper issue hiding in the reality of autonomous deployment. We are putting neural networks in charge of 2-ton machines on public roads.
Yeah, and the streets are messy.
Very messy. What about the regulatory and ethical guardrails for all this?
Well, the SAE's AI committee is actively developing standards for safe deployment. But there is a ton of real-world friction. NHTSA recently started scrutinizing robotaxi safety protocols after a Waymo vehicle got stuck and actually delayed emergency responders.
Oh, man. And that edge case failure perfectly highlights one of the most provocative discussions from the sources, I think. An industry voice brought up the limitations of process compliance frameworks like ASPACE.
Yes, this is such a fascinating point. Let's really dig into this.
Yeah, because ASPACE basically dictates software process quality, right? It ensures you documented your code, you tested your code, and you followed rigorous engineering steps. But this post argued that process compliance cannot guarantee ethical engineering intent on its own.
Exactly. And they cited Dieselgate as the ultimate cautionary precedent for this.
Oh, that makes perfect sense.
It is a profound point. Because during Dieselgate, the engineering process was likely impeccable. The code was clean, the testing was thorough, the documentation was perfect. Process compliance was achieved.
Right.
Yet the system was intentionally designed to deceive emissions testing. The framework only audits how you built it, not the morality of what you built.
And if auditing explicitly written rule-based code failed to prevent an ethical disaster like that, how do we possibly audit the ethics of an AI-defined vehicle?
That is the exact friction point the industry is running headfirst into. Machine learning models don't use simple if-then rules. They use inference. They are just massive webs of weights and biases.
It's statistical.
Yeah. When an autonomous system makes a split-second decision to swerve away from a pedestrian but hits a parked car, it isn't executing a pre-written ethical script. It is calculating statistical probability based on its training data.
It's a total black box. You can have a perfectly compliant ASIL development process for your AI model, but if the training data contains inherent biases or the reward function prioritizes the wrong outcome, the car behaves unethically in the real world anyway.
Exactly. A process checklist cannot validate the moral alignment of a neural network.
Which is exactly why the regulatory bodies are struggling so much. You can't just open up the code to see if the car will make the right ethical choice. The transition to AI-defined vehicles means shifting from auditing code to auditing behavioral inferences.
And that is a science we haven't fully mastered yet.
It is a staggering hurdle for the industry to clear. Process compliance just does not equal moral compliance.
It doesn't. And as we look at the macro evolution of all these challenges, from the decoupling architectures to ASIL safety to the ethics of inference models, we are really witnessing a much larger convergence happening.
A convergence with what?
We'll leave your listeners with this thought. The automotive industry and the robotics industry are no longer separate fields. They are actively converging around the development of physical AI and humanoid technology.
Oh, because whether you are building a humanoid robot or a level 4 autonomous vehicle, you are fundamentally trying to solve the exact same foundational problem, right?
Precisely.
How does a machine process sensory data and navigate a chaotic physical world autonomously?
Exactly. And as a result of this convergence, memory and storage suppliers are quietly signing these massive strategic agreements in the background. They're acting as the new kingmakers right now.
Really? Memory suppliers?
Yeah, because they are the only entities capable of meeting the sheer immense compute needs of these intelligent physical AI vehicles. The ultimate battle isn't just about who writes the best software anymore. It's about securing the silicon and memory that makes this physical AI possible in the first place.
Wow. It's just a fundamental rewrite of what it means to be an automaker. If you enjoyed this episode, new episodes drop every 2 weeks. Also, check out our other editions on charging and battery tech, commercial fleets, and autonomous and mobility markets. Thank you for joining us today. Keep pushing the boundaries out there, and don't forget to subscribe.